सर ऑडियो थोड़ा इसमें माइक लग गया तो बेहतर होता सर.
आपके इन से कहेंगे ये जो भी आएगी. Okay, the LMS site is not up yet. They are working on it, so it will be up where the slides and other related content will be posted, inshallah. So people who are registered, I think they will be automatically added to the LMS site. Those who are not registered, I think they should write their email, the email that they want to use for registration to be added to the LMS site. So if one of you can volunteer, can you do that? Just take a sheet of paper and circulate it. So whoever wants, they can add their. So write your name, first name, last name, and email. Okay. Any questions before we start? अभी आपको बिल्कुल नहीं आ रही ऑडियो या कुछ आ रही है?
कुछ आ रही है सर.
ठीक है, let's start and okay. So I'll pick up from where we were last time. In fact, I'll go a few slides back and start from there. So we started our discussion, which is the first topic in the course. We started our discussion of 2D geometric primitives. When I say 2D, I mean an image. That's because in this course we will talk about both 2D spaces and 3D spaces, right? Because a camera essentially is the mapping device from 3D to 2D, right? It takes a projection of a 3D world to 2D. So we will talk both about 3D and 2D a lot and the transformations between them. But we are starting off by pure 2D, so there is no 3D mentioned right now. Every point is on a plane. So every point is on a plane. Okay? So that's what I mean by 2D. And in 2D we are going to talk about primitives like points, lines, and connects and so on. Okay? So that's where we are starting our discussion from. So I talked about 2D points yesterday. A 2D point is in the normal Cartesian coordinates that you are used to. A 2D point is written as a 2 vector, and by convention we are using column vectors always. So it's written as a vector x tilde y tilde. I use a transpose just to save space. Okay, a transpose just like this. So that's just to save space. And it belongs to R2, which means x and y are continuous numbers here. The reason I'm using tilde here is because we will soon distinguish between homogeneous and inhomogeneous coordinates. So we write the normal inhomogeneous coordinates with a tilde and the homogeneous ones without the tilde. So the coordinates that you are used to before, the Cartesian coordinates on the Cartesian plane are going to be written with a tilde. Okay? So now we introduce the concept of a different representation for these points, which are homogeneous coordinates. These are vectors that are equivalent up to a scale. Yani any vector that differs by a scale only, a single scale factor only, is actually the same point on the plane. Okay? And so we are going to write points x, and notice I dropped tilde because that's the normal convention that I'm going to use in this course. Normally we are going to be talking about homogeneous vectors. So at some place, for convenience, we might switch between homogeneous and inhomogeneous, and that's where the tilde will kind of give you a convention of what we are doing. Okay? So this point x is x, y, w now, whereas it was x tilde, y tilde previously, and it belongs to this space of 3 vectors. This space of 3 vectors to represent 2D points, right? Vectors of length 3, but they are still representing 2D points here, is called P2, which is the projective space, okay, as opposed to R2. Now, P2 is quite similar to R2, because we can represent all the points in R2 in P2 also, but we can represent a few more points. So there are a few changes in P2 with respect to R2 that I'll count. Okay, is that okay? All right. So let's talk about P2 now, which we started doing last week. Okay. So a point, for example, 10, 21. Okay. okay, this is an additional coordinate now, is the same as a point 30, 63 or a point 5, 10, half. These are all, as vectors they are different, but as representation of a point they are all the same in V2. Okay? And the reason for that is what I wrote here, that vectors that differ only by a scale are equivalent to each other. I'm not sure what's the capacity of 10302, so we might need to change it again. Is there a sheet being circulated? So just make sure everyone writes their email on it, so if there is an announcement or something, I can contact you. In fact, oh wait, one more thing, sorry, so you might need to send it back. Why don't you guys add, if you feel comfortable, why don't you add your WhatsApp number? So what we can do is maybe make a WhatsApp group, and then announcement can circulate more rapidly. Okay, anybody who doesn't, it's optional, so anybody who doesn't want to do that, they're free to not. Okay? So maybe you can send this sheet back and then it starts again. Alright. Okay, so these points are equivalent, and this tells me that every physical point on a plane in R2 can be written actually in an infinite number of ways in this new space. Because I could choose really any real factor as my scale factor, it will just be the same. And so this space is called P2 and it's the 2D projective space. Alright? So I gave this example last time. We have this point 5, 6 on the Cartesian plane in R2. It can be written as maybe 10, 12, 2 in P2. It will be the same thing. So a homogeneous vector X, which means a vector in P2, can be converted back into the Cartesian space, the inhomogeneous space, just by dividing by the last term, because that is kind of the scale factor. Okay, so which means if I write the homogeneous vector X as x, y, w, this is also really w and then x tilde y tilde 1, because if I take w as common, then 1 is your the kind of the normalized scale factor is 1. Because multiplying, dividing is the identity, so multiplying, dividing by 1 doesn't matter. And so x tilde really is x over w, y tilde is really y over w. Alright, any questions around this? Okay, so what we have really done is we have by this slide really, we have defined a new type of mathematics that you have not seen before. This is called projective mathematics, right? Just a word of caution here that people trend, in the beginning, people tend to treat mathematics as some sort of absolute truth, right? You learn tables in school and you say 2 times 2 is 4, and you just, that it solved is that, right? And that carries on throughout mathematics. You just learn that this is how it is. There is no argument over it. But essentially, at its very nature, the nature of mathematics is that it's based on some axioms, right? All branches of mathematics are based on some certain fundamental axioms. So you define some axioms, and based on that, you get that form of mathematics, right? So the 2 times 2 is 4 is actually starting from the base 10 system, which we built on our fingers, and then we realized, okay, what would addition mean, and so on. So we defined what is addition, and we moved on from there. When you start studying probability theory, you first study like 3 or 4 axioms, and then the entire probability theory books and books of it are based on those axioms. So what happens there is, really, you define those axioms, and then you say, if this is true, then this must be true, and if this is true, then this must be true, and you keep developing that mathematics, right? So that's what we have kind of done here. We have defined a new vector representation. This is just by definition. There is no truth to it. There is no fundamental reason to essentially do it this way, and somebody can come up and say, no, I'll have a different vector representation, and then they'll build a different mathematics. It turns out that if we do it this way, in the homogeneous coordinates, in the P2 space, rather than in the Cartesian space as we're used to, we end up with certain simplifications in certain forms of equations and so on, which are very crucial in computer vision. So it turns out that we can we can do more simplified mathematics of camera. Okay, and I'll talk more about that. Okay, but this concept should be absolutely clear of how I define a homogeneous vector.
So why are they called homogeneous coordinates?
Because of the equivalence of classes, I think, right? So all the vectors in that equivalence class are similar to each other. Okay. We use the same term, for example, in homogeneous equations, which are equations of the form Ax is equal to 0. And that equation also has the same characteristic that up to a scale factor is the same. You can multiply by any k and it doesn't really matter. The solution that you will find of Ax is equal to 0 as a matrix equation will be up to a scale factor only. You can't find a precise solution unambiguously. Whatever solution you find, the scale factor of that will also be a solution. So the term homogeneous is used in that sense in mathematics, things which are equivalent up to a scale factor. At least that's the best I know. Maybe there's some other reason.
I think it's the homogeneity property.
Superposition. Which is coming from the equivalence classes, yes. Okay? Alright, so then, since I have defined a new space, there are some consequences that follow from these axioms, right? Again, a slide we already covered yesterday, but I want to do this again. So consider the homogeneous point 4, 2, 1. It is a point in P2, but I know from my previous slide, I know how to convert points in P2 to points in R2 on the Cartesian plane. I can only draw R2, I can't really draw P2. And I'll come to why I can't. Okay? Because P2 contains some infinite points also. Okay? So whenever I need to draw, I can do my mathematics in P2. Whenever I need to draw, I can come back to my familiar R2 space, which is the Cartesian plane. Okay? So I take this point in P2, which is a vector 4, 2, 1, and I'm going to convert it into a point in R2. So how do I do that? I take this last term and I divide the first two by that. Well, in this case it's just 1, so that's 4, 2, so I can plot it. Okay, that's the process I will use to plot points. Okay, so I can plot it, that's the point 4, 2. By the way, just a note about axes here. I said in images x goes this way and y goes this way, right? But here I'm drawing it this way, but that's okay because it's just a rotation of the whole thing. I didn't do any flips to do that. So whether you think of the image or you think of the Cartesian plane, they are actually equivalent to each other. I mean, if you have an image and you just look at this way, it will be the Cartesian plane, right? So there's no difference. Okay? Alright. That's actually an important point because some books don't use that convention. They say people are used to, in an image, x going this way and y going this way. And actually that makes it a flip from the Cartesian plane, which means your equation of line changes. The gradient of +1 now is going to go the other way. So the role of x and y actually gets a mirror image of each other from the Cartesian plane. And I don't like that convention. That's an unnecessary complication to do. So we always say row column x, y in the image, and that's the simple way to do it. Okay? Alright, so what about this point? 4, 2 and a half. Because you are dividing by half, it becomes 8, 4, so it's here. What about 4, 2 and a quarter? Well, this will be here, right? And what about 4, 2, 1, 8? Notice I'm just reducing the scale factor here. So that's going to be here, right? And that means limit w tends to 0, 4 to w is going to be infinitely far away. Okay? Now, so points with w is equal to 0 are called ideal points. They are points at infinity. As far as P2 space is concerned, they are just like normal vectors. Because P2 space is vectors of the form A, B, C. And yes, C can be 0. There's nothing forbidding that. So as far as P2 space is concerned, points at infinity are almost like, well, they are like normal points. In R2 space, that's kind of problematic, right? Because you can't draw infinity on a Cartesian plane. But in P2 space, you can treat it mathematically. You can treat mathematically infinity as a very normal concept. Okay, the infinity will manifest itself when you convert this from P2 to R2. That's when the infinity will manifest itself. But before that conversion, it's just like any other vector. So we call them ideal points or points at infinity. And these points actually define a direction from the origin, because you see, all the points, when I was changing the scale factor, making it smaller and smaller, all the points were along this direction. And this is the direction defined by the first two coordinates, 4 and 2. Okay, so it's 4 along x, 2 along y. That's the ratio that defines the direction for you. If I change that, it will change direction. So now we have a concept of directional infinity, right? Infinity in this direction, infinity in that direction, infinity in that direction. So these infinities, one way to think about it, even though it's not the correct way, I will counter that in just a moment. But one way to think about it is that infinities surround the Cartesian plane. Okay? So it's actually slightly problematic to think like that. So I'll show why that's a problem. Yes.
So is there an infinity coming out of the page?
No, there is no out of the page. It's a two-dimensional space. So an ant will just crawl on this world, on this carpet. It can never fly. So there is no third dimension. Again, that's a loose, because ant is a 3D structure, but that's a loose analogy. Yes.
If we convert these ideal points back into the R2 space, can't they lie anywhere in the R2 space?
No,
So
no, let's try doing that. Right? Let's try doing that. What about 4 to 0? To convert 4 to 0, I'll say 4 divided by 0, which is infinite, and 2 divided by 0, which is again infinite. Right?
So that's the points in P2. So when we convert it back into the R2 space.
No, that is the conversion in R2 space. To convert in R2, I divide by W. I divide the first 2 by W. So when I divide the first 2 by W, it comes out to be infinite. Right? So the point is that infinity in the Cartesian plane, I can't draw it. That's all I'm saying. Right? Infinity is not a Cartesian plane concept. Yeah.
Sir, when the point starts from 0, 0 and we make the third particle of a vector 0, so is the infinite line going to be all in all directions, or?
Yeah, that's actually where we stopped last time, right? The question was, you can do that for all points, but what about the origin itself? And yeah, that's a problem. Let me come to that. It is a problem. Yeah. So far, so good for all these green points that I drew. But what's the direction of origin? The origin doesn't have a direction. Yeah. By the way, these points at infinity do not have a non-homogeneous equivalent. They do not have a Cartesian equivalent. Okay. All right. So this is. I'll come to your question in just a moment. So this is the projective space P2. I've just defined a new projective space. Yes.
So even in R2 we can find the direction by the equation of lines.
Yes, yes. I'm not saying there are no directions in R2. There are, definitely. I'm saying in P2, those directions are encapsulated in these ideal points, because ideal point only encodes direction, because it says this way, infinitely far away. So it doesn't encode a position, because infinitely far away is not a precise position. So ideal point says this direction but infinitely far away, this direction but infinitely far away. But that's not to say that there's no notion of direction on the Cartesian plane. There is, obviously. The concept of slope is the concept of direction. And interestingly, if you write a line equation as ax plus by plus c is equal to 0, what encodes the slope? The first two portions of this vector ABC, which is also what is happening here. The first two portions, the first two coordinates in the 3 vector is encoding the direction. Okay. So it's not terribly different. It is almost the same, but slightly different with some important changes. Okay. All right. So let's now look at this projective space P2 more formally. Every coordinate is defined by a 3 vector. By 3 vector, I mean a length 3 vector. So every coordinate is defined by 3 vector x is equal to x1, x2, x3 transpose. Okay. And the first two of the elements of the vector define the direction only, because notice all the points that I wrote there were in the same direction, because the first two were the same, 4, 2, right? So the first two, x1 and x2, define the direction only outward from the origin. And therefore, coming to your question and what we ended at last time, the point 0, 0, 0 does not define a direction. It's problematic. It doesn't have any direction. So we exclude it from P2. We say that's not allowed. That's how we define P2. P2 can be any vector except for 0, 0, 0.
So what about 001? Wouldn't that be the same?
No, 0, 0, 1 is very interesting. Counting that. But 0, 0, 0 is not. Okay? So P2 is really R3. Now notice first time I'm talking about R3. Because what is R3? R3 is all possible vectors that are of length 3. Right? So I'm saying P2 is really R3. This minus is set exclusion. It's not actually negative, it's set exclusion. So I'm saying one way to say this is P2 is all the vectors in the world that you can possibly write in as 3 vectors, which is R3, except for the vector 0, 0, 0. Okay. And the set of points in R2, so this is one way to think about P2. Another way to think about P2 is really all the vectors in R2, all the set of points in R2 written as equivalence classes in as a length 3 vector, added to that all the ideal points. Okay? Because ideal points were not there in R2. So there are 2 ways that I can think of P2 in my mind. I can think of P2 as all length 3 vectors except for origin. And of course as points, there will be multiple representations of a point in this. Or I could say all the points written as 3 vectors and the ideal points. Because the ideal points were not in R2.
So isn't this the opposite way around?
What?
The set of points in P2 should be those that are in R2, augmented by ideal.
Oh yeah, maybe there's an error. Oh yeah, sorry. Thanks for pointing it out. The set of points in P2 can be thought of as a set of points in R2 augmented by ideal points. Yes, you're right. Okay, so one question that comes to mind is why are we doing this? I mean, we had learned vectors in school and then in university and so on, and all of a sudden we are defining a new space. I can't fully answer that right now because as we progress in the course, you will see a lot of simplification of mathematics, right? But I don't want to pen that and you never get to see it till later. So I want to give you a small hint about why are we doing this type of mathematics? Why are we building a new form of mathematics here than what we are used to? And there are actually 4 reasons for that. Okay, the camera itself is a projective engine, which means the camera itself is an engine that follows rules of projective geometry. There are, for example, straight lines mapped to straight lines in a camera. That's a fundamental definition of projective geometry. And so we will see that if we use this form of projective mathematics, it's more in sync with how a camera works. Okay. The points at infinity are handled gracefully. A camera can see till infinity. Right? Whenever we look at the horizon, okay, we see horizon as a defined line, but actually it's a collection of points at infinity, right? Because they are infinitely far away, or points infinitely far away will map to a horizon. If I wanted to draw a point infinitely far away on this plane, this carpet is a plane. If I want to make a drawing here, people who are familiar with drawing would know this, right? That if I want to, as this point goes more and more away and I'm drawing it in a picture, which is the 3D to 2D mapping, the points which are infinitely far away will be drawn on the horizon line, right? So in a camera is sort of like a projection device where points at infinity in the real world become finite in the camera. Okay. A horizon line will have finite coordinates, but it's actually representing in 3D points which are infinitely far away. So we do need to deal with points at infinity. And this projective mathematics deals with points at infinity in a much more graceful way than Cartesian mathematics, where you have to write them as limits and so on. Okay. To deal with infinity in the Cartesian space, you have to use the concept of limits, and it's more cumbersome. Okay. And the main advantage why I'm using it here, otherwise I could have just spent it in some future courses, that the algebra becomes much simpler than usual. And also, it's one of the most general frameworks to work in as opposed to some other spaces. So the Cartesian plane that you are used to is an Euclidean space. And then we can talk about a superset of that, which is affine spaces. We'll do that later. And then projective space is a superset of affine spaces. So it's like a more general representation than there. I want to show you just a preview of why the algebra is simple as usual. Take a simple camera, sort of like surveillance cameras we have in this room, right? And a surveillance camera can kind of rotate, and so it can pan and it can tilt, right? And it can change its zoom level. That's pretty much what it can do. So we call these PTZ cameras typically, right? So if I were to write an equation of a PTZ camera, what do I mean by an equation of a PTZ camera? An equation of a PTZ camera means that what that equation should do is that you give me a point in 3D world, you give me coordinates of a point in 3D world, and I'll tell you what should be its image coordinate in that camera, right? So that's what a camera model or an equation of that PTZ camera would be. If I write that in your normal Euclidean mathematics for this camera, it comes out to be this, okay? If I write it in, so don't try to copy that because it's just too much, right? But if I write it in projective mathematics, I can write it as a simple matrix equation of x is equal to px, where this p is specifically a 3x4 matrix. And x is a 3D vector, this is a 2D vector. So just a simple matrix relating 3D and 2D vectors. The world vector with name. Okay? So that's reason enough, right? Unless you want us to deal with these types of, and then manipulating them mathematically is much more complicated because there are these cosine theta and sine theta terms and so on, so much stuff going into this. All right. So in a way, actually the fundamental point here is that this relationship between capital X's and small x's, small xy and capital XYZ, is a non-linear relationship. Right? Because there's a division involved. So there's a non-linear relationship between them. Here we have a linear relationship between them. Because matrix multiplication is a linear operation. Then you study all these types of things in linear algebra, it's linear operation. Okay? In fact, what really happens is that there still has to have a division for you to compute the coordinates. But that division is the last division you do by converting from homogeneous to inhomogeneous. So you bend that division till the end. And you say, I can do all my mathematics without that division. And that will be linear. Because the non-linearity was being introduced by that division. Okay? Alright, so properties of the camera can be derived simply from this camera matrix P in projective mathematics. For example, the location of the camera is just the right null vector of P. Recall what is a null vector? We'll do a linear algebra tutorial maybe tomorrow, inshallah. There's a tutorial scheduled for tomorrow, so we'll do a linear algebra tutorial tomorrow where I'll go over some of the crucial linear algebra concepts that are needed for this course. So, but a null vector is just a property of this matrix. It's mechanical to compute it. And the location of the camera is just the null vector of this matrix P. The location of the camera in the 3D world coordinate system. Okay, so things become simple like that. Simple operations on these linear equations can be done. Okay, so I introduced this new concept of homogeneous vectors. So having done that, let's look at some of the familiar things. So what have I done? I've defined how you will write a point in this space. Okay, so the next crucial concept is a line. Okay, so let's look at how you will define a line in this space. Okay, so what's the equation of a line in Cartesian space? That we are well familiar with. Ax plus by plus c is equal to 0. X, y here are the Cartesian coordinates, and a, b, c are the parameters of the line. In fact, a and b together define the direction of the line, which is the slope minus b over a, and c is related to the intercept on the y-axis of the line. So really, a and b define the direction of the line, and c somehow defines the location of the line in some sense. Okay? you are well familiar with that. So I can represent this line as a vector because the parameters of the line are not xy, they are ABC. So I can write it as a vector ABC transpose. Okay, good. Now notice that this vector is the same up to a scale. By same I mean the line does not change if I multiply ABC by a single scale factor k, right? Because the other side is 0, so you could just divide by k that side, and this side it's the same, right? So which means the ABC line and k times ABC are the same line as long as k is not 0. Agreed? Which means that the set of all possible lines is really R3 minus 0, 0, 0, R3 with exclusion 0, 0, 0. Because 0, 0, 0 does not define the line. Every other vector in R3 defines the line. Okay, 0, 0, 0 would be that case when you got k is equal to 0, so you multiply that by a vector, you excluded that. And which means the set of all possible lines is all the vectors in R3 except for 0, 0, 0, because that's not a line. But that precisely is the definition of P2 space. So line vectors are naturally representable in P2 space.
And how are lines defined which have the argument 0, 0 and the third argument being any non-zero argument?
That's okay, that's a line.
How is that a line? How does that project onto the...
I'll show you in just a moment. I'll show you in just a moment. I mean 0, 0, 1 is a valid line actually. Not in Cartesian space, but in our space it is a valid line. It's actually called the line at infinity horizon. I'll come to that in just a moment. Okay? But so far you are right that I'm saying exclude origin, but why am I not excluding things which are other than origin but they contain a 0, right? Like 0.401. That also includes a 0 in it, and so there is a problem there. But we'll see that no, that's not a problem. Okay.
So when we multiply k with the vector, isn't c going to be multiplied with k? And if c is going to be multiplied with k, then the line is going to be above the line.
No, not at all.
Because
If I changed c alone and did not change a and b, then the line is going to move. So if I just have a line x plus y plus 1 is equal to 0, and I write 2x plus 2y plus 2 is equal to 0, they are exactly the same line, right? There's no difference. That's what I'm saying. Multiplication. Okay, so lines are represented by vectors in P2. In fact, you did not know about P2 space before, but this is the way you have been representing lines. So it's actually a natural representation to represent lines. Let's talk about now, because we talked about points, we talked about lines, let's talk about a point on a line. How do I tell in P2 space whether a point is on a line or not? So a 2D point is in homogeneous coordinates it's xy. Okay? The point, I'm just doing normal mathematics now just to revise, right? So a point will lie on a line if and only if I plug in xy into the parameters of the line and I get 0. Which means you give me an xy and I have a line ABC, I'll just plug it in and see whether I get 0 or not. All the points that lie on the line must give me a 0. That's why it's called an equation of the line. No other point which does not lie on the line should give me a 0. Every other point in the space will have some other value other than 0 if I plug it into the left hand side, right? That's why it's an equation, because it precisely defines every point in the line. I mean, this condition is true for every point on the line, and it is not true for any point which is not on the line. That is what an equation means, right? Okay, so now you are familiar with this equation. I'm just going to write this equation as a dot product. Okay, of xy 1. I added a 1 because there was no xy with c. So xy1 dot product with abc equal to 0. Do I have the transpose the right way? Yes. Okay. So what does this mean? It just means a times x plus b times y plus c is equal to 0, which is what the equation is. So I'm just writing it in a vector form rather than otherwise. Okay. So what does this really mean? ABC is line L, so let me write it with a boldface L as vector L. Okay? So I'm saying xy1 multiplied by L, which is ABC this way, is 0. That's the equation of a line. Agreed? Everyone is okay with that? So, and any non-zero k can be multiplied to this point, and the equation will not change. Okay? Which means I can, instead of writing xy1, just directly following from this equation in inhomogeneous space, instead of writing xy1, I can write 2 times xy1 like I did here, and it will be the same line. Okay? Hence, not only can I represent the line in a homogeneous vector, I can also represent this point as a homogeneous vector because the scale factor of k doesn't matter. And so the equation of a line is really x transpose. Now this x is a P2 vector because I augment it by 1 and I can multiply by k the whole thing. So x transpose L is equal to 0. That's the equation of a line in P2 using P2 type of points x. Okay? Previously what was it? It was xy dot product with AB of the line because that's ax plus b plus a c. There was an additional c there. Now because of that additional 1 that we have in xy, that c is also incorporated within the dot product. So the equation of the line actually simplifies to a simple dot product between the point and the line. But the only thing is that this point is now a P2 point, which means it's a 3 vector. Okay? So even though x and L are 3 vectors, I have a comment here that they have 2 degrees of freedom each. What do degrees of freedom mean? We'll talk about this a lot in this course. So what do degrees of freedom mean? Anyone? Any idea?
Coordinates can change.
Which can change independently, right? So a line has, if I'm writing a line has 3 parameters A, B, C. But actually, if I talk about a particular line, only 2 of them can be chosen independently, because the third one, since the scale factor does not matter, I could always say that I am choosing the one which is c is equal to 1, and then that becomes these 2 coordinates. Okay? I can always write this line as some a prime, b prime, and 1, and so there are 2 parameters here. Okay? The fact that scale factor does not matter reduces a freedom for you from the length of your vector. Okay? So that's why when we talk about lines, we talk about m and c, 2 values, slope and intercept. We don't talk about a third value because m and c, 2 numbers are enough to describe a line. Similarly here in the normalized form where c is equal to 1, 2 numbers are enough to describe a line. Same way for points. In a point, that scale factor does not matter, so I can always convert it to kind of a normalized form where that last scale factor w is 1, and then 2 are enough to define that point. Which is how it should be because I'm talking about a 2D space, so 2 coordinates should be enough to define a point. Okay? So that's what I mean by this comment. Even though x and L are 3 vectors, they have 2 degrees of freedom each. There are 2 independent parameters in each one of them. Alright? Okay. So this is the point x, y, 1 and it lies on the line ABC only if the dot product of these vectors is 0. Alright, let's talk about another construct. I talked about a point on a line. Let's talk about 2 lines intersecting at a point. So I'm given 2 lines A, B, C, D, E, F, and they will intersect at some point x, y, 1 or kx, ky, k. I want to find that point. So 2 lines will obviously intersect at a point. Let L and L prime be 2 lines. They are given to you as input, L and L prime, and they intersect at a point x. Then, how do I find x? And so my claim is that I can just take the cross product of L and L prime and that will be x. That's not how I do in my normal mathematics. In the normal mathematics, I solve these equations simultaneously to find x, right? But actually this is similar. You just have a mechanical operation of cross product here today, okay? So everyone remembers cross product? Yeah, how do you compute cross product if you have L1, L2, L3, and you have L1 prime, L2 prime, L3 prime, The mechanical way to compute it is that you say I, j, k, and evaluate this determinant. It will evaluate it into something I plus something j plus something k. That vector will be the cross product vector. Okay. So really the property is that it's orthogonal to the two vectors. If you think of it as in a space. Okay. So my claim is that you can find this point x just by the cross product of the coordinates of those two lines that are given to you. What's the proof of that? I'm going to prove this because it's a new thing that I stated. So I'm going to prove this. So here's the proof. The point x lies on both L and L prime. Yes? In fact, that is how it is defined as the point of intersection. Therefore, it must be true, since x lies on L, then x transpose L must be 0. That's the equation of the line. And since x also lies on L prime, then x transpose L prime should be 0. That's the equation of the line. And this, both of these dot products being 0, is non-trivially possible. I mean, there is a trivial solution, x is equal to 0, but that's not what we are interested in. They are non-trivial solution only if x is orthogonal to both L and L prime, right? Because the dot product of two orthogonal vectors is 0. Recall that from your algebra, right? So if x is so the lines are on the plane. If x is orthogonal to L and x is also orthogonal to L prime, then it must be going orthogonal to that plane. Okay, which is what is given to me by the cross product. Okay, and so this completes my proof.
So how can you take the dot product of two column vectors?
No, I didn't. That's why I wrote the transpose. X is a column, L is a column, so I said X transpose L. Okay, so it's like X transpose becomes like this, L becomes like this. So this is a way to write the dot product. I could write X dot L, which is exactly the same as X transpose L. Okay, so in general, A transpose B, if A and B are column vectors, is a dot product. And the result is a scalar. Okay? So summary, to find whether a point is on a line or not, you can just take the dot product of that line, at that point with the line vector. If the point is defined in P2, that's how we will work now. And given two lines, you want to find their intersection, you just take the cross product of those two lines. Already you see that the mathematics is being simplified. And the reason for that is that the point and the line are now vectors of same length, so you can manipulate them in a matrix algebra way. Okay. Yeah.
So this xy1, the x1 is orthogonal to these two lines. And
Yeah.
it must not lie in the plane.
Yes.
It is out of the plane.
In the Cartesian plane, yes, it is out of that plane. That's true. But as coordinates, if you treat them as coordinates, it's the coordinate of the intersection point.
But its direction is not in the plane.
Okay, let me describe. If I think of the P2 plane, which I haven't really said that, if I think of the P2 plane as a plane, but then every point has a scale factor with it, then yes, this direction is this. Okay, but when I convert this 3 vector into a 2 vector, it will feel like a normal point on the Cartesian plane. So then it has its own direction on the Cartesian plane, not an orthogonal direction to the lines. That's why I'm not drawing a picture of the Cartesian of the P2 plane yet, because it's not like really possible to do that in a nice way. Okay, another problem. We are just building our construct so we can get familiar with this mathematics. If I'm given 2 points, the opposite problem of that. If I'm given 2 points and I want to find the line joining them. So I'm given x and x prime, these two, and I want to find what is ABC. Let's try to do that. I'm saying 2 points must lie on a line. So let x and x prime be the 2 points that lie on the line L. Okay. Then x cross x prime gives me the line L. That's my claim. Okay. Looks awfully similar to what we saw on the last slide, but these are points, and I'm taking the cross product of those points, but points defined in P2. Okay. So proof, the proof is also awfully similar. The line L by definition, the line that I'm after by definition passes through both x and x prime. Therefore, x lies on that line, so L transpose x is 0. X prime lies on that line, so L transpose x prime is also 0. So L transpose x is 0, L transpose x prime is 0. L is the same now, the point is different, which is non-trivially possible only if L is orthogonal. L is a vector which is orthogonal both to x and x prime, which is given by the cross product. Really nice and simple. I don't know if you appreciate it or not, right? But there's a beauty here. Right. I mean, in fact, I think about it when I do this. I say, why did we learn the old mathematics and did it that way? We should always have done it this way. I mean, in school they teach you this is a vector, this is how it works. Why don't they teach it this way? We've done away with R2 forever. Okay, so there is a duality here that I want you to see. So x and L look awfully similar. They are both 3 vectors. In fact, they look exactly similar. They are both 3 vectors and both can't be 0, 0, 0. And both don't change if you have a scale factor with them. If you multiply them by a scale factor. So they are both in the PQ space. Okay? So x and L are kind of similar. In fact, it's not just they are kind of similar. If you give me a space, if you give me a sheet of paper in which you draw a lot of lines, okay, I can build an equivalent sheet of paper, another graph paper in which I draw a bunch of points, and there will be there will be dual to each other because every line I can convert into a point, and so this space will be kind of like a dual to the other. Okay, look at the equation of the line. So x transpose L is 0 is an equation of a line, and I can switch all the x's and l's, and L transpose x will also be an equation of a line because dot product is commutative, so it doesn't really matter, right? And then x cross x prime equal to L. Yani you give me 2 points, I will take their cross product and I'll get the line joining them. And exactly in an equivalent way on the other side, if you give me 2 lines, I will take their cross product and it will be the point at the intersection of that. In fact, in projective mathematics, we don't treat joins and intersections as 2 separate concepts because of this. There is one word for them in projective geometry, which is a join. So we say 2 lines join at a point and 2 points join in a line. We don't say an intersection is something different than a join because that's a Cartesian concept. In projective geometry, that's not necessary because it's equivalent. Okay, so this is called, from here we get the duality theorem. I'm just mentioning for interest, it's not terribly important for this course, but just to complete this discussion. So any theorem of 2-dimensional projective geometry, you come up, you do your math and prove and do your PhD and you come up with some nice result in the end of something that you have proven about 2D projective geometry. Okay? So any theorem of 2-dimensional projective geometry, there is a corresponding dual theorem that can be derived simply by making all the points lines and all the lines points. Because points and lines are kind of equivalent and interchangeable in some sense. They are not equivalent in the same space. In the same space, obviously a line is a join of infinite number of points. But there could be a dual space in which that line will be one single point. And a point here will be a line in that dual space. Okay? So it's kind of like a sale that you have, buy one, get one free type of thing, right? You're doing your PhD and you prove a theorem and then you'll have 2 theorems of projective geometry. As soon as you prove one theorem, you will have another one. Okay, that's what duality means here.
This is only valid for like linear lines and points,
Actually, it's valid for the entire projective space, so duality holds.
curves.
So in conics, in quadratic equations and so on, in everyone, because everything is constructed from the point, and the point is dual to the line. So the entire space has a dual equivalent space. Projective geometry, by the way, just for your interest, is a discipline in mathematics. People study it as a field. It has 2 traditions. So there is projective algebra and there is projective geometry. There are people who just use geometry to prove theorems and so on, and then there are people who do exactly the same thing but just in algebra. Okay. We are taking just an application view here, so we are not studying projective geometry for its own sake and trying to get a comprehensive treatment of that. We just picked a few things out of projective geometry literature just so that it is enough for us to understand cameras. Okay? Alright, any questions? Okay, so let's talk about some more concepts then. Okay, we are just building our understanding of this mathematics and this space. Okay, so I can keep throwing new and new problems at that have to do with points and lines. Now we have a concept of parallel lines, right? But lines which have the same slope. So consider two lines, L is equal to AX. Notice my pattern here. I always start from the familiar mathematics that you have and then derive the equivalent in P. Okay, so there are two lines L, AX plus BY plus C is equal to 0. So ABC, that's the line L, and ABC prime. Notice I didn't change A and B because if I changed A and B also relative to C, then that would have been a line in a different direction, so that's non-parallel. So parallel lines means they have the same slope, they only differ in their intercept. So if L prime is parallel to L, then A and B are same and C prime is different in your normal mathematics. Okay? So I have one vector ABC and another vector ABC prime as two parallel lines. Right? Okay, so if I want to see where they meet, these parallel lines should intersect somewhere. Well, any two lines should intersect somewhere, and so parallel lines should also. Some people in their school define it like parallel lines are lines that don't meet. That's correct. I mean, but it's not very satisfying. Why? Because even at that time you could think of the concept of infinity this way, that these two lines will meet here. If I rotate it to become more parallel, then they'll meet further away. If I rotate it more to become more parallel, they'll meet further away. So then in the limit that they're exactly parallel, they'll meet at infinity. Okay? And that's kind of like the Cartesian way to think about it, because infinity has to be treated in limits. But here it's no longer necessary. I mean, points at infinity are normal. And let's see how that works. So I'll compute the intersection. I just given two lines. I forget that they were parallel. Let me just compute their intersection normally. And how do I compute their intersection? I can just take their cross product. And you should work this out just so that you are comfortable with this. That way that I said, how do you take a cross product? So if you take the cross product, it comes out to be the C prime minus C becomes a scale factor and it becomes B minus A0. Okay? So that's the intersection of ABC and ABC prime. Just by taking cross product. Okay? So therefore the point of intersection is, because the scale factor doesn't matter, the point of intersection is just B minus A0. For projective points, K doesn't matter. Okay, so C minus C prime was common in all of them and we just took that out. And so the point of intersection is just B minus A0. Yani I can write a projective vector as any scale factor, it will be equivalent. So I chose to make this one. Okay, is that okay? Everyone is okay with that?
So again, this is infinity, so this is not really a point.
In the projective space it is. That's the new way to think about it. I mean, in the projective space it is. And yes, parallel lines should have met at infinity. So had I gotten anything other than 0 here, I would have been uncomfortable with that, right? How come just by changing the notation I reached some fundamentally different result? So it must have been 0, the last point.
So can you please explain the computing intersection part?
Okay, sure. Let's go here. Okay, so two lines, and what is the input? Two lines, L and L prime, ABC, DEF, general, two lines. Okay, I'm saying, first I make the claim, then I prove it. My claim is that to compute the intersection point X is just the cross product of L and L prime. Okay, now, the point X lies on L and L prime, by definition, because it's an intersection point, therefore X transpose L must be 0, because that's how a point lies on the line. And X transpose L prime must be 0, because it lies both on L and L prime. And that means that L, in a non-trivial way, I mean, the trivial solution to both these equations simultaneously is X equal to 0. But that's not the solution we are interested in. 0, 0, 0 anyways is not a point in projective space. Okay, so the non-trivial solution is that this vector x must be, because it's orthogonal to L and it is orthogonal to L prime, it must be orthogonal to both L and L prime. And vectors which are orthogonal both to L and L prime are scale factors of the cross product only. And scale factors don't matter, so I can say it's just a cross product. Okay? Good. So, going back. So I just did nothing extra. I just took two parallel lines, computed their cross product to find their intersection, and I ended up with an ideal point. And in fact, it's an ideal point in a particular direction. And in fact, if you find that direction, it's the same as the slope, minus b over a. Right? That's how you would find the slope of this line. Yes?
So can you do the cross product on the board of this particular equation?
Okay.
And can we see how the zeros are?
Let me do that. I, J, A, B, C, A, B, C prime. Okay? So how do you do cross product? I first take the cofactor matrix of this. So B, C prime minus B, C, right? Then with a negative sign, I take the cofactor of this. So A, C prime minus A, C. And then with a positive sign, I have to A, B minus AB. So AB minus AB is obviously 0. And here CC prime and CC prime, so C minus C prime is something I can take common out of this because this is B and B, this is A and A. So minus A and minus B and minus A. Okay? This is what we wrote here. Alright? Okay, so I can convert this to inhomogeneous coordinates if I want to. So it's B over 0 minus A over 0. That's the inhomogeneous equivalent. And so, which is a point at infinity. I mean, anything divided by 0, unless that anything is 0 itself. So anything divided by 0 is infinity in normal mathematics. 0 over 0 is undefined. It's not infinity, right? So when I convert this to inhomogeneous coordinates, it's a point infinitely far away in the direction given by the slope of minus b over a.
So isn't division by 0 also undefined?
No, not at all.
So it's only
This is a very important, sometimes misconception comes. Division by 0 of a finite number, which is non-zero itself, is a defined concept which can be understood by limits.
Yes, that's what I was going to
So it's not undefined, it's a defined concept which we understand. It's a defined concept, but it's a difficult concept, so we understand that concept by limits. If I say 5 divided by 1, I know it's 5. Then I say 5 divided by half, so it's a bigger number. 10, then I say 5 divided by a fourth, so that's an even bigger number. So 5 divided by the limit w tends to 0, w is a limit infinity. In this limit w tends to 0, this is infinity. So this is a defined concept. But 0 over 0 is not a defined concept in mathematics. You can't get around it, no matter which way you think. Okay?
So I was just going to say that 5 by 0 will also be defined only in the limit.
Yeah, it is defined in the limit. So that's how you normally do in mathematics. That's why in first semester you have to take this course on limits and that's why you have to do this. Before you study calculus, you study limits, right? Because a lot of things in calculus are also defined by limits. Why? Because there is a division by 0 inherently in calculus, right? How is the derivative defined? Limit delta h tends to 0, f of x plus delta h minus f of x divided by delta h, right? So you have to do this division by 0, or almost 0, right, to define a derivative. But this is, I mean, there's nothing wrong with that. We do it all the time. When you say the derivative of x squared is 2x, you are actually doing this. Okay. All right. So therefore, we are saying we reach this conclusion that if you agree with this new concept of inhomogeneous coordinates, then parallel lines must intersect at ideal points. Okay? which are points at infinity, and that's what we knew before also, that parallel lines should not meet. When we said that, that really meant that they should meet at infinity. However, notice that I did not do any special mathematics to reach that conclusion. The way I'm computing intersection of parallel lines is exactly the same way as I should compute intersection of non-parallel lines. So points at infinity are like nothing special in projective mathematics. Okay? Alright. Now here's a bit of a twist where your brain kind of takes some time to get around this. So there are a bunch of ideal points, right? I choose any A and B and put a 0 next to them, and that becomes an ideal point. And so I said, there are ideal points in this direction, and that direction, and that direction, and that direction. There is an ideal point for each direction. And so I said, maybe the ideal points surround the whole Cartesian plane. But it turns out that there is a bit of a flaw in that picture. The ideal points actually lie on a line. The set of all ideal points lies on a line itself. Okay? Do you understand the confusion here? Okay. But I mean, that's what mathematics is. I said I will define some axioms and then I will just keep deriving the consequences of those axioms. Okay, and this is actually a consequence of what I defined very innocuously on the first slide. I said, oh, we'll treat a vector by augmenting it by 1. Right? I mean, defining P2 spaces. This is a consequence of that. Now, let's see. Recall that all parallel lines, well, you don't have to recall far away, it was on the previous slide. Recall that all parallel lines intersect at an ideal point. Okay? And the point at infinity is of a form x, y, 0. That's an ideal point. Okay? Alright. So consider two such ideal points. Okay, maybe the ideal point going in this direction and the ideal point going in that direction. So there are two different ideal points, two different x and y's. Okay, so the first ideal point is x is equal to x, y, 0, and the second ideal point is x prime is equal to x prime, y prime, 0. Both are ideal, both are points at infinity. Now I have 2 points. I can join them to make a line. I know how to do that. How to do that? Take their cross product. Yeah. So let's find that line. Let's make a line by joining x and x prime, which will be just x cross product with x. If I do that, it turns out that L is equal to 0, 0, and then this term. Okay, try doing that, just like I did it here. Try doing that. I get 0, 0, and this term. I can take this term out common because the scale factor doesn't matter, and therefore it becomes 0, 0, 1. Okay, so that's the line joining two ideal points. By the way, consider here that even this notion was nonsensical in Cartesian mathematics. I can talk about infinity in Cartesian mathematics, but I can't talk about joining two things at infinity. That does not make sense in Cartesian mathematics. But here it does. So, because the ideal point is like any other point, and so I can join 2 points at infinity now, and I get a line there. And so, since I took 2 generic ideal points there, this actually holds for all ideal points. So, this is the result. Thus, all points at infinity lie along a single line. And so this is a line which is the collection of all points at infinity, so we are going to call it line at infinity, which is L infinity equal to 0, 0, 1.
So if this is the line at infinity, what would be the corresponding point 0, 0, 1? Was it?
That's a dual space. In that dual space, that's a point 0, 0, 1.
What would that be represented in the Cartesian plane, the origin?
Yes, the origin is the Cartesian plane, because 0, 0, 1, 0, 0, 2, 0, 0, 3, they're all equivalent, and that's the origin.
And if I were to imagine the single line, would it be like a circle-ish line around the...
What is a circle-ish line?
a line being a circle.
A line is not a circle.
But a line being a circle, like tilting...
A line has a finite, has a single defined slope. A circle doesn't. The
But like
change
if
of
the plane is like this, the line does have the same slope in this plane, and it's forms a circle around the...
It's not working out. You're trying to do something, but it's not working out. Right? Okay, so I have a picture for that. I don't want to draw it. I mean, like I said, whenever the notion we follow is that we'll keep doing projective mathematics, but whenever we need to make a drawing, we come back to inhomogeneous coordinates. the problem with that notion is that you can't draw infinite things on inhomogeneous coordinates, okay? But there is a kind of half a picture that I can draw for you. And that picture is this. So this is your Cartesian plane. So I take a direction and talk about the infinitely far away point in this direction, and let's say that infinity is here. It's not, but I can just draw it, okay? And now I take another direction, and in that direction that infinity is here. Okay, and I take another direction, and in that direction that infinity is here. Notice I'm changing the length to infinity, right? I'm changing it, but that doesn't really matter. Infinity times 2 is also infinity. Okay? And then, so this is like here.
What about the lower axis?
Well, this direction is also just the opposite of that direction. So maybe I can draw a line at infinity here and a line at infinity here, and then say, well, they're kind of like equivalent because it's like the negative of the other. This is not a correct picture, so keep that in mind. But I'm just showing you why there might be a notion of a line. But that doesn't really matter. What matters on this slide, I've done no fraud while deriving this, right? So if you believed what was on the previous slide, I just consequently defined it. The problem you were saying that the circle is kind of a line is that the circle keeps changing its slope at every point, whereas a line doesn't. A line is a constant slope construct.
So, what about these lines at infinity?
Sorry?
We have just derived that these two lines at infinity, would they meet at infinity point as well?
No. See the notion of infinity. Let me say that the positive infinity and negative infinity notions are, you are kind of familiar with that. When you talk about that the slope, what do you say? What is the slope of y-axis? Yeah, you say the slope of 0 is this, slope of 1 is this. What's the slope of this? It's infinity, right? But how do you get that it's infinity? Well, you do slope as rise over run, right? But you keep reducing the run, right? So you keep reducing it, and in the limit that run is exactly 0, the slope is exactly infinity. But whether you do it by rotating this way, you will get infinity, or by rotating, take a negative line and keep rotating it from the negative side, the slope, right? You'll still get infinity. You can say that it's that way or this way. This notion does come up in mathematics. When you are drawing equations of tangent, right, the graph of a tangent, how come by going to infinity this way, it continues from this way? Where did that switch happen? Okay, so I mean, you have seen this notion that things switch from plus infinity to minus infinity depending on whether you are approaching infinity from the positive side or the negative side in the limit. Because 0 is neither, positive or negative, it's at the same location. And that's, so you can approach 0 from the negative side by reducing negative numbers down to 0, or you can approach it from the positive side by reducing that limit from the positive numbers down to 0, and then you'll still reach infinity. So that shouldn't be too much of a concern that we are drawing two lines here. And by the way, I said I shouldn't have drawn it. I'm just trying to give you some sort of analogy picture. Otherwise, fundamentally, I can't draw it.
But in a sense, this makes sense because if you collapse,
It's good if it does. Go ahead.
because if you collapse a circle, you reach a point.
Yeah.
So you are encircling the whole space.
I think the tangent interpretation here is very relevant because that's what a tangent does, right? Doing the rise over run and then compressing the run down to 0, and you can do it for a triangle this way, or you could do it for a triangle this way. So the switch from positive side of infinity to negative side is natural. Okay. When you draw a graph of a tangent, you see you go all the way to infinity and you come from minus infinity back. Okay, so now we have a new line. You did not know about this before, but we have a new line. It's called line at infinity. So let's start studying this line. Let's start studying this line. So any line ABC will intersect the line at infinity at b minus a0. That's my claim. Okay. Any line, we have kind of done that claim on the previous slide. Any line parallel to L, which is L prime, so if it's parallel to L, it should be A, B, C prime, will also intersect line at infinity at b minus a0. You could verify this now. It's very simple to verify, and in fact line at infinity is only 0, 0, 1. So the 1 multiplies by the last term, so it doesn't really matter. Okay. In inhomogeneous coordinates, this b minus a represents a direction. That's the slope, right? That's how you would compute the slope. You would say the slope of this is minus b over a. Hence, the line at infinity is nothing but, so as the direction of a line varies, its intersection with the line at infinity varies. If two lines are in the same direction, that is they are parallel, they will intersect at the same point at line at infinity. Okay? So the line at infinity is nothing but a set of directions on the plane. It's a set, it's a collection of directions, all directions. You put them together and it becomes that line at infinity. Let me conclude quickly in 2 minutes by an example. So here's a picture. I mean, I've been talking about mathematics and so on, and you say, like, this is a computer vision course, for God's sake. I mean, we should be talking about images, right? So I just put some examples here as images of how you would use these calculations. Okay? So I took an image which has a lot of lines. Here, go ahead. Right? This is from this Wikimedia page. So this is just a zoomed portion of that. Okay? So I pick a point. I'm now going to write it as a 3 vector, not a 2 vector, remember? Okay, so this has some coordinates, x and y, and I pick another point. Okay, so this has another coordinates x prime and y prime, measuring from here, the top of the image. And then what will I do? I want to find a line. So how will I find that line? Think of the code you will write. You'll just write, you'll use, let's say, a linear algebra library or code a cross product thing. It's a simple thing, and you'll just take those 2 vectors, find their cross product, and you'll find the line joining them. Okay, now you have this line, and you find another line, you'll join them. Again, I say join them, which means intersect them, which means you'll again compute their cross product, and you'll get the point of intersection. You can take this line and that line, and they are parallel, so they must intersect at infinity. How will you do that? You will again do the same calculation. You can take this line and this line, they are parallel, and how will they intersect? They will intersect at infinity. And in fact, infinity this way and infinity that way will also lie on a line which is the line at infinity. Yeah. The line at infinity has an infinite number of infinite points. I should say, because it's a line, how many points does the line have? Infinite. So the line at infinity is a collection of infinite points, infinite number of points. Each one of them is an ideal point. So it's the infinities, right? The collection of infinite points. Okay, so I can do the same thing with this line. Let me extend it. I extended it, and this line I extended. So these 2 lines are intersecting at this point. How would I compute that intersection? Again, by the cross product. And it gives me a finite point, but this point actually defines a point which in real world should have been at infinity, right? Because in real world, these 2 tracks were parallel. So on that plane where all these tracks are led, that point actually is at infinity. Okay? But in my camera, it's appearing as a finite point. And I can take these 2 lines, and I can compute their intersection, which is, I think, about here. and that also is a point at infinity on this ground plane. And therefore I actually did that, so I got this, and then I can join them. And that's a line at infinity for that plane. So I said you can't draw it, well I drew it. I drew the projection of it. Okay?
So ये असल में parallel है in the P2 plane parallel नहीं है.
Think of this ground plane as the P2 plane. Of course, in my image, that's not the P2 plane. In the image, it's the image plane of the camera, where you have the film or the CCD array. Okay? But in the real world, I'm saying that was a real point at infinity. In my projection, in my drawing, it's not coming out to be a real point. So those who are familiar with drawing know this is how you draw 2-point perspective drawings, right? You first pick your points along the horizon as the vanishing points, you call them vanishing points in drawing, and then you draw from there so that you get the correct perspective. In fact, this was, by the way, this discovery of perspective was not trivial. I mean, mankind spent a lot of centuries to discover this, that this is how you make correct drawings. It was actually during the Renaissance. By the way, this line, in normal terms, we call it horizon, right? So in In this scene, you don't see it, but that's your horizon. In fact, this geometry was discovered by Brunelleschi in about 14th century, 15th century. Before that, people did not know how to make correct perspective drawings. So if you look at artwork from, for example, Chinese scrolls of the old, they don't have correct perspective. He was an architect and he discovered this notion of a vanishing point. And this is actually from his book. So you see exactly the same drawing as what I made on the previous slide. And he wanted to build a cathedral, and so he drew a sketch of that cathedral as an architect, even before he built it. And this is now a picture of that cathedral, and you see that they are in such close alignment because he knew how to project things. All right, there's a question somewhere. There was a question somewhere. Yeah.
पिछले पिक्चर में अगर कोई और सेट ऑफ पैरेललाइज देते हैं, फॉर एग्जांपल अगर विंडोज से पैरेललाइज दिखाते हैं, तो वो जिस पॉइंट पे वो लाइन मीट करी तो that wouldn't form the same line as this horizon.
Excellent question, right? So we are talking about P2 space. So this is a P2 space makes planes, right? So this ground plane is a plane. That face of the windows, that building is a plane, but that's not the same plane as this ground plane. So that, if I want to find the line at infinity of those, that will surely be a different line at infinity than this one. So when we talk about horizon in our understanding of just general English word horizon, we are always talking about the line at infinity of this ground plane. But if there was a tilt and there was a building or something, and then the lines meeting for that will be on some different line, right?
But all these parallel lines, all the points where parallel lines of all the different windows meet, both are the same horizon.
They will be, so the question is, if I draw lines this way and draw lines this way parallel on this plane, yes, they will meet on some other ideal points, and those ideal points will make some other line. That line will not be the same as this blue line because it's for some other plane. Now in Cartesian space, we have 3 orthogonal directions, right? Like this ground plane, that one, and that one. So we have 3 orthogonal directions. So you could think of 3 lines at infinity.
3 different horizons.
We don't call it horizon because horizon fundamentally is from horizontal.
Okay.
It's this one. So I won't call that the English word horizon, but it will be a line at infinity. And then you can think about where those line at infinities will intersect. We'll leave it at that. That's a good call.